Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise. We're going to practice a lot of stuff. So we're trying to find the volumes of solids generated by revolving different regions about different lines or axes. So we have four problems to consider. Essentially we have in fact three different regions to start with, R1, R2, and R3. And those regions are made of four different curves. One is y equals x squared. That's the blue curve. That's the parabola. And y equals x is the red line over there. And y equals 0 is the x-axis. And also y equals 1 is also a horizontal line here. So if you look at, for example, R2 is made of two curves. One is y equals x. The other one is y equals x squared. That's the region bounded by these two curves. And R3 is the region bounded by this vertical line here, x equals 1, x-axis, and the blue curve. And R1 is made of this horizontal line, y-axis, and the red line, y equals x, okay? So in the first case, we're going to revolve R1 about x equals 1. X equals 1 is the vertical line here, so R1 is going to be revolved around x equals 1. In the second case, R2, that's the aqua or turquoise region, revolved about y equals 1 horizontal line. So we're going to have the revolution like this. And R3 is going to be revolved around x equals 1, which is right here. So x equals 1 vertical line of revolution. And finally, we're going to revolve R3, the same light blue region, about y equals 1 horizontal line. Okay? So, and we're going to use the disc or washer methods, depending on what the question is relevant. But this is going to be a long video, and I'm going to split it by 4, so you will see each one of those cases in separate videos. All right, let's get started. All right, let's start with part A. So we have R1, the red region, revolved around x equals 1 vertical line. Okay, so let me just have the cleaner version of this. And here we go. X equals 1 is this vertical line here. Let me just use a different color. Okay. And this is where, this is the axis of the revolution. Okay. So we're going to use the disc or washer method, but in both methods, we take a slice from the region strictly perpendicular to the axis of the revolution. So let's have a representative slice here from the red region. Let's say like this comes with thickness dy because it can't be dx because the bottom part or the very left end of the slice touches the y-axis, so that thickness is determined by or labeled as like dy, okay? And let's say like this slice here is y units far from the x-axis, okay? So essentially, whatever the volume formula that we're going to write, that should be involving dy. So everything is going to depend on dy, okay? So let me just move this a little bit down here. And this is already R1, so I can erase this portion here. Okay, there we go. So I'm going to revolve this region around, okay? I'm going to revolve, this slice around, okay? Let's see what we get. So here we go. And from this moment, I can't use black anymore because that's not going to be able to see. Let me use yellow. How about that? There we go. And this comes with thickness dx, okay? So to be able to write down the volume of this washer, I need the inner radius and the outer radius. Okay, so the inner radius is determined by here, so I'm going to call it little r. And the outer radius is this length here, right? And that is capital R, okay? And capital R is, as you see, fixed, because no matter what slice you pick, it's going to be exactly equal to 1. The distance from the origin all the way to x equals 1 vertical line. That's always 1, okay? And the little r is determined by the line, and line comes with the formula. Line comes with the formula y equals x. So if the y coordinates of that is y, so it's just going to be y. So x coordinate is y. So essentially, this part here, and maybe I don't know if you can see it here. So this length here is going to be just y. Okay. So for that reason, since capital R is 1, little r is going to be the total length from the y-axis to the vertical line, which is 1 minus what we found to be that distance here, y. Okay. So 1 minus y is little r. Okay. All right, now I want to go ahead and write down the volume formula. Okay, let's try to write it down. There we go. Volume is going to be pi. I'm going to check the limits of the integration next. But this is r squared minus little r squared dy. Okay, let's go back to the formulation. In the red region, all the y's are in between 0 and 1. So y's are ranging in between 0 and 1. So I go back and I put the lower limit to be 0, upper limit to be 1. I will also put capital R and little r back down there. So 1 minus, so 1 squared minus 1 squared minus 1 minus y quantity squared dy. Okay. All right, so let's simplify this. So this is pi, integral from 0 to 1, 1 minus 2y plus y squared dy. And that is equal to 2y minus y squared dy. Let's find the antiderivative in one shot. So pi y squared minus y cubed over 3 from the power rule of integration. Okay. Let's plug in 1 and 0 for y. If you plug in 0, by the way, that's going to be 0. 1 minus 1 over 3 minus pi times 0. Okay? So this takes you to 2 over 3 pi. Okay? So this is taking care of part A. And for part B, please move on to my next video. I'll see you there.